So for an example of this idea, let's go back to the market entry game. So the story was you had one firm in the market, firm 1, and then firm 2 could decide to enter or not enter. If firm 2 plays not enter, the game ends and firm 1 collects their monopolist profits. If firm 2 picks enter, firm 1 can charge either a high price, and they both share profit, 4 and 4, or firm 1 can charge a low price, ignite a price war, and both firms become unprofitable. So payoffs are firm 1 on top, firm 2 in the bottom. So our rollback equilibrium is we go here. If we're at this node, firm 1's going to play high instead of low. They'd rather get 4 than get -1. As a result, firm 2 knows that if they play enter, then firm 1's going to play high, getting a payoff of 4. If they play not enter, they get 0, so it's better to enter. So the rollback equilibrium is that firm 1 plays high price and firm 2 plays enter. We know rollback is also called subgame perfect Nash equilibrium, so let's just add that. Rollback / SPNE. Now, we also saw what happens if you try to convert this into a simultaneous move game and find the Nash equilibrium with your best response analysis. So let's see. Let me squeeze it in over here. So let's make firm 1 our row player, charging high or low. And then firm 2 is our column player, playing either enter or not enter. They play not enter, the game ends, and firm 1 gets 10, firm 2 gets 0. If they play enter, H gives us a payoff of 4, 4, and L gives us -1, -1. And we do our best response analysis. So what's firm 1's best response to enter? That'd be to play high, because 4 is better than -1. If firm 2 plays not enter, doesn't matter, you get 10 either way. Now I'll find what is firm 2's best response to high. It's better to play enter and get 4 than play not enter and get 0. What is firm 2's best response to low? That'd be to play not enter and get 0 instead of getting -1. So we have two Nash equilibria. High enter, which is also our rollback equilibrium, and also L not enter, which is not rollback and not SPNE. So here we'll see a connection between rollback and subgames. If we go back to our game tree over here, we have a total of 2 subgames. We have this subgame here, starts at a single node, breaks no information sets, and then we have the whole game subgame. So to be subgame perfect, this Nash equilibrium has to be a Nash equilibrium in both these 2 subgames. So we already know what happens in the big subgame, the whole game subgame. We already analyzed that over here. So 2 Nash equilibria, high, enter, and low, not enter. So now we'll show that this second Nash equilibrium, low and not enter, is not subgame perfect. So I'll convert this smaller subgame here into simultaneous move form. It's a very trivial subgame, only one player making one of two choices. So this subgame is going to look like the following. So we have firm 1 picking high or low, and firm 2 has already picked enter. And the payoffs are 4, 4, and -1, -1. So firm 1's best response to enter is to play high. Firm 2's best response to high is to play E because that's the only option. And firm 2's best response to L is to play E because, again, that's the only option in this smaller subgame. So in this subgame, the only Nash equilibrium strategy is HE. So the equilibrium we had in the entire game, the second equilibrium, L not E, is not subgame here because L is not a Nash equilibrium in this smaller subgame. So this is basically a refinement upon Nash equilibrium, saying you can't just be a Nash equilibrium the whole game, you also have to be a Nash equilibrium in every subgame. Why we impose that extra restriction? Well, if you do not impose, if you go back to just a regular Nash equilibrium concept, then what happens is you have Nash equilibria that are effectively sustained by a non-credible threat. So here's what I mean by that. If you go back to our game tree, so I was saying before my phone ran out of space for the video, I was saying that this other Nash equilibrium, L not E, is based on a non-credible threat. So if you go back to our game here, here's what's going on. So firm 1 is saying, if you play enter, I'm going to play L. Firm 2's best response to L is to play not enter. So if firm 2 really did believe that firm 1 is going to play a low price, then you better off playing not enter and getting 0 rather than playing enter and being stuck with -1. So firm 2's response of not enter is a best response to the low price. Low price is also a best response to not enter, because if firm 2 plays not enter, then firm 1 gets 10, and that's the best possible outcome. So it is a Nash equilibrium. The problem, though, is that when firm 1 threatens, I'm going to play L, that threat should not be believed. That's because if firm 2 just played enter anyways, and firm 1 is stuck over here at this node, it's better than to play H and get 4 rather than play L and get -1. Firm 1's just basically hurting themselves by playing low instead of high, so when they're saying they're going to play low, you shouldn't believe them. They're actually going to play high. So in that basis, firm 2 should not believe firm 1's threat to play low, which means that as a result, firm 2 is not going to play not enter, so this won't happen. So arguably, this Nash equilibrium, low not enter, is unrealistic. That's why we refine our criteria by looking at subgame perfect Nash equilibria to see if we can rule it out. So it turns out that whenever you have a Nash equilibrium that's not subgame perfect, then there's always some non-credible threat involved. So that's how it works for the market entry game, but you can see many other examples elsewhere as well. So for another example of non-credible threats, we're going to look at what's called the grenade game. That one's up on the slide, so we'll stop the video here and do a sequel with the slides.